All right, everyone. Let's begin for the day. So this is the second class where we won't really be doing a whole lot of programming. Today is the day where we talk about binary, hexadecimal, that kind of thing. So I have a bunch of lecture slides on the material. I might pull them up right now. Yeah, I'll pull them up. There we go. Nope. How about this one? Yes. Okay. So put that up there. This can come here. Okay. Can you use return for lab 7? I would think so. Especially if you can use functions. So, okay. Basically here, we're going to learn how to convert numbers from binary to decimal, from decimal to binary. We might do a little bit of we might be doing a little bit of addition, subtraction, multiplication. I guess I can look at lab 7. I don't know. Let me check lab 7 right now. Oh. Right, okay. So, the reason why... Yeah, so it says don't return anything. So, I guess the theoretical... Like, I'll say this. It's like return isn't banned in the same sense, right? It's not like on the forbidden list. But these functions shouldn't return anything. And that's kind of the way that it... Because like this one shouldn't return anything because it's just printing some stuff. And this one shouldn't return anything because the documentation says... Well, you can return none. Oh, you can... I mean, if you type the word return, that'll get you out of the function. Yeah. But also just not returning will do the same thing. Because at the end of the function, it'll return. So, I mean, there's... I guess I'll say this. Like, here's a common practice that some people use, and let me just show you. Where do I have it? Here. So, here's a common practice. So, let's say define a function. Let's say that the function is going to be something like test prime. Well, let's not do test prime because that'll actually have to return something. Let's say, you know, what's a function that does something? Good question. Do something, right? And let's take a list. And then let's say that, like, what we're going to do is we're going to say, like, a list 0 plus a list 1, maybe 2 times, plus a list 2, right? We're going to return this. So, like, this is the something, right? This is more code here. But let's say that you know that this is going to break if you're not going to have 3 elements in the list, so you can always just be like, if not a list, return 0, for instance. So this is a common practice to do this, because what this will end up doing for you is this return is kind of like, what it does is it gets you out of the function before you do anything bad. Which means, like, anything bad could be, you know, accessing indices that don't exist, etc. So this is kind of a common practice. You know, are you allowed to use not? Of course. Of course. Return none is sort of hidden in the end of functions. Yeah, so return, basically the way to think of it is like, if I don't put this into a function, there's a secret return none here. And so you don't actually have to type this. It will just happen. Because if you remember that what we're going to do here, let's put in do something, maybe the list 1, 2, 3, so it's not going to punch out here. And so if we print this out, what we're going to see is that this should print out. Okay, why does it not like me? Oh, okay. So you see here, it's going to print out none. No, return to get out of a function is totally allowed and recommended. If you want to use that kind of feature, sure. Like this is totally allowed, not discouraged at all. In fact, like Python kind of likes this because it prevents you from having a bunch of nested statements, for instance, because the alternative to this is generally like if a list, and then what you do is you do, like, you know, you do stuff on a list, and then you have an else, you know, return 0. And so this is the other structure. It honestly, I don't think it reduces the runtime. I don't think that is, no, I wouldn't say that. I would say the only difference between these two things is that all your code here is now going to be at like nesting level 2, I guess, right? Because it's nesting level 1 because of the function and another one because of this if statement, whereas this code here is at nesting level 2, but then the rest of the code here, this is just nesting level 1. And so, I mean, sometimes it's prettier, sometimes it kind of avoids sticking everything into, you know, higher degrees of nested loops and stuff like that. Anyway. Okay. So, let us actually talk about the class material for the day. First, I'm going to take a drink of water. Alright, that's done. I can return from the drink water function. Okay, so when we look at decimal numbers, there's something about them, right? So here is 153. 153 is equal to 3 plus 5 times 10 plus 1 times 10 squared. And if you guys are familiar with base 10 expansion, this is exactly what that is, right? So in the ones place, you have a 3, right? Technically times 10 to the 0. You have 5 times 10 to the first power, and you have 1 times 10 to the second power. So that's how you split numbers apart. So like this, technically you might even think of like a number written as 153. It's kind of like a shorthand. It's kind of like a an abbreviation for this expression here, right? Because this one is actually saying 3 in the ones place, 5 in the tens place, 1 in the hundreds place, and that's it's important to understand this before you go on. So that's why I'm spending 2 minutes talking about it. All right, so let's see. So 729, which is an entirely interesting number. I think it's a pretty great number. So basically, we split it apart in the same way. It's 1 times 10 cubed, right? 7 times 10 squared, 2 times 10 to the 1, and 9 times 10 to the 0. And so you see that each place has its own power, and each place has its own digit. And so the digit is going to be between 0 and 9, and the power is just going to go up in order, right? It's going to be 0, 1, 2, 3. And of course, we would have to remember that 10 to the 0 is equal to 1. So that's how we get this kind of expansion. All right. So this is a base 10 number system, right? It's the way we count, because as it turns out, we have about 10 fingers on average. So that's why we have a base 10 number system. We kind of think in tens. Everything we've built around is in tens. But, okay, so basically I did that for a longer number, so 281-853-47922, right? So it's almost like a phone number, it's just even longer. It's not particular anything, but you see that here I've split it down into each digit, so each digit is listed here, each power is listed here, and the 10 to that power, I call it the factor here. I mean, it's basically the exponent, whatever you want to call it, right? I mean, power, I guess, is exponent. It's like 10 to the exponent. I guess I just needed to come up with a name for that. You could almost call it place, right? Like the hundreds place, the thousands place, the 10,000s place, the 100,000s place, etc. So this is how we break down numbers. So, as it turns out, binary works the same way. Well, yes, okay, I'll just say that. Binary works the same way, except that instead of the base being 10, so everything is the same, except for the base is now 2 instead of 10. So that changes two things, right? First, it changes, the powers stay the same, because it just goes 0, 1, 2, 3, 4, 5, all the way up. So the powers aren't really modified, but what do get modified are these factors or exponents or whatever you want to call them here. 2 to the 0 is equal to 1, 2 to the 1 is equal to 2, so this would be the tens place, but now it's the quote-unquote twos place, right, or something like that. This is the fours place, this is the eights place, this is the 16s place, 32s place, 64s place, and 128s place. So, right, so that's, and then of course I'm about to talk about this sentence. So the two modifications. One, it changes these things that I'm calling factors, which I probably shouldn't call factors. And then the other thing that it changes are instead of being digits, right, because a digit is a decimal digit, right, with D means, base 10. This is you could call it like a bidget because it has, a binary digit, but they just shorten it down to bit, right? So, so instead of a digit, we have a bit, and the limitation is you have to remember that the bits can only be as high as the base. So what I mean by that is that bits can only be 0 and 1, right? And you see why bits can only... So you see why binary is kind of useful for a computer, right? Because in a computer system, at least for now, unless we do quantum computation and have some kind of entangled state business going on with a vector representing our qubit state or something, basically, unless you have something really complicated, computers are basically like Basically they're on or off, right? You have a piece of wire in a computer, and even if that piece of wire is just one transistor that's like 5, 10, 15 nanometers across, whatever, it doesn't matter, right? Either it has some voltage on it or it doesn't. And so if it has some voltage on it, usually we call that 1. If it doesn't have voltage on it, we call that 0. And it would be difficult to have like additive voltage things. We would need things that are other than transistors. We would need like capacitors and all kinds of resistors and all kinds of complicated systems in order to get multiple values out of electrical stuff. And so generally we just use ones and zeros to represent ons and offs. And so that's why we use binary, right? Binary comes out of necessity. It's basically like the computers require us, the engineering processes that build computers require us to well, the computer senses zeros and ones basically by using like transistors and gates and stuff like that. So the way a transistor works is that basically you have two inputs and an output, and if you put current onto, I forget if it's one of the terminals in the transistor, then it'll allow current to flow through the transistor, and if you don't put current on it, then it'll prevent it. And there's other transistors that do the opposite. So basically, you can kind of build, the simplest thing you can kind of build out of them are like and or gates, and then you can build not gates and stuff like that. And once you have gates and memory, right, and you can build memory by kind of chaining transistors together in things that are called SR flip-flops and stuff like that. Once you do all of that, then you basically have a computer that's like a computer in the sense of Turing. Where I mean, when I say Turing, I mean like Alan Turing, right? Or Alonzo Church. Okay, so let's do a few basic examples. So what is 0110 in decimal? So let's write it out. I have a document up here. Right, so 0110, let's pull up my it is where is my LaTeX? It's in like render, that's where it's, I always forget where they've hidden it. Okay, so 0110, and I'll put a little underscore for binary, is going to be equal to, it's going to be equal to 0 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 squared plus 0 times 2 cubed. Why is it only 4? Well, so it doesn't have to be really anything in particular, right? So, are you going to render or are you going to explode? Okay. Let's hope this rendered somewhere. Cool. So here's an example of a binary number. Basically, this binary number is 0 times 2 to the 0, plus 1 times 2 to the 1, plus 1 times 2 squared, plus 0 times 2 to the third. And so when we add all this up in total, this is going to be 4 plus 2, so this is going to be the number 6. All right. Let's see how that rendered. I think that should... There we go. So, okay, cool. So let's do another example. 110, 110. So 110, 110. I'm sorry, 1100, 1100. So basically we have to start reading from this side, right? And we say that this is equal to 0 times 10 times 2 to the 0 plus 1, right? Times 2 to the, I'm sorry, 0 times 2 to the 1 plus, and then finally we get to a 1. We get 1 times 2 squared plus 1 times 2 cubed, right? And then I'll do this on the next line, I guess. Maybe we'll do this. We'll continue this on the next line. Plus the same thing, except now with some higher powers. So, so this would be 2 to the 4th, 2 to the 5th, 2 to the 6th, and 2 to the 7th. And so basically, we're going to write this out in let's see here. So it's 1 times, so it's 2 to the 7th plus 2 to the 6th plus 2 to the what? 3rd plus 2 squared. Whoops. Don't want to do that. Okay. Try again. As it turns out, if you have errors in your LaTeX, it will not do. So you see here, I've omitted all of the zeros. I've only added the ones together. And so, here, 2 to the 7th is 128, 2 to the 6th is 64, so that's 192 overall. 2 to the 3rd is 8, 2 squared is 4. So this should be, if I'm not mistaken, this should be 204, if I did this correctly. So let's see what happens. I'm going to say it's 204, and then I will, so I'm going to say the answer, and then I will check it with trusty old calculator to make sure I'm right. Because who knows, if I'm wrong, then I'm wrong. Okay, cool, 204 is correct. All right. So let's do another one. Sure. So what's the difference between this one and, for instance, let's just do, so what's the difference between these two numbers? And so we're going to see that, I don't know why it always puts it so far away, but, so what's the difference between these two numbers, right? 11001100 and 10101100. So what's the difference between these two numbers? Really, you can see that all we've done is we've shifted a single term, a single number, a digit, or bit, I guess I should say, to the right by 1. Well, I mean, so think about it, think about that question, right? So you're all at home, and, you know, I'm not forbidding you to use computers, and computers have calculators on them, so you are perfectly allowed, all right, to use a calculator if you want. Okay. Yeah, so it should be something like 176 or 172. Let's think about that for a second. It should be whatever this one is minus 32. Because, so yeah, 128, yeah, 172 I think is right. So Yep. Is it possible for it all to be zeros or ones? Yep, it's totally possible. I mean, if you have a number that's, let's look at an example for instance. Let's say if we do something like this. Here's a bunch of ones. So what is this number equal to, right? This number is equal to 2 to the 0 plus 2 to the 1 plus 2 squared plus 2 cubed plus 2 to the 3rd power plus 2 to the 4th power plus 2 to the 5th power plus 2 to the 6th power plus 2 to the 7th power. And then I have to count. So I did 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I did exactly 10. Or I guess actually I did 11, but... And so, here's the thing. Whoa. That's way too much for a single screen. But there it is. Maybe I'll remove the... I'll remove the page border. Okay. Yeah, so... Yeah, so this is going to be 2047, and the reason why I'm pretty sure that that's right is because there is a fact in math. That fact says that the sum from I equals 0 to, say, n of 2 to the I is equal to 2 to the n plus 1 minus 1. So here's a little fact. And this fact basically tells you how to add up. It tells you how to add things up, right? So, okay. Yeah, so basically the way to think about this equation here is that, for instance, yeah, you're right. So this is, we would call this a geometric sum. Basically with the... There's a more general formula. I'm sure that if you've taken Calc 2 already, you know that general formula, or at least you've seen it. But for our purposes, this is all we really need. Okay, and you don't even technically need this formula. I'm just saying that this is why all the ones, when you add up all the ones, I don't actually do this calculation. I just say, okay, 2 to the 10th is equal to 1024. 2 to the 11th is equal to 2048. So this whole thing should just be 2048 minus 1. And if you redo the calculation, you'll see that that's true. So, and it's still true for things like, for instance, if you do something like 11 in binary, which I really shouldn't call 11, but 11 underscore b is really 2 plus 1, right, which is equal to 4, 2 squared minus 1, which is equal to 4 minus 1, which is equal to 3. And you see that the equation is at least true. It's at least true there. Right, so it's at least true in the case of what some people, so we kind of call this like 11 in binary, but really you should be calling it, like it's the decimal value 3, right, because it's 2 plus 1, or it's equal to 2 squared minus 1, or it's equal to 4 minus 1, or it's equal to 3. Any way you cut it, it's equal to decimal 3. But there we go. Okay. So here's another one. We can just add this one up. So this is 1 plus 2. And then we get the 4's place, 8's place, 16's place, and 32's place. So 32 plus 2 is 34. Plus 1 is 35. So that's how you add these up. So for instance, I guess it's 1 with 3 zeros, 1, 1. Let's make the font twice that size, is equal to 32 plus, whoops, oh, it's zooming instead of doing a plus sign. Okay. So, we've talked about converting binary to decimal, but what we haven't talked about is converting decimal back to binary. So here's a bunch of other examples that I'm not going to do. So how do we convert from decimal to binary? And I mean, I only threw this joke in because it's like, I usually do it to just make everybody kind of groan in class, like, ugh, this again. Unfortunately, we're not in class, so I can't hear what you have to say about this joke. The good news is I don't really, it doesn't matter. But yeah, so there's only 10 types of people in the world, ha 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 ha, right? But of course the thing is that this 10 is the binary 10, which represents the number 2. Yeah, I mean, it's a topical joke, right? Topical humor, people. Topical. So, all right. So I think the easiest way to think about converting from decimal back to binary is to think of it as code. And so let me write the code and explain it as I'm doing it. So in order to actually do the conversion, at least in Python, we need to pretend like the thing that we're going to take in is a binary number, but we're going to take that in as a string. And the reason why we're going to take that in as a string is because if we did, for instance, if we said, oh, let x equal to 1001100, this is the problem. This is not a binary number. This is decimal. You know? So in order to be able to output it, let's just keep it as a string of zeros and ones. And then what we're going to return is the decimal value of that string. Oh no, I'm sorry, we don't want to do that. Decimal to binary. The parameter is going to be this time it's going to be a number. And it's going to return the binary string. Yes. Okay, that's the way I want to go. Sometimes I forget which way I'm going. So here's how to convert from decimal to binary. So you know how to convert from binary to decimal now, right? You just add up the powers of 2 that are represented. But how do you convert from decimal to binary? So let's find out. Let's do it. So basically here's the rule. How do you convert? Or let's think about decimal numbers. Let's think about decimal numbers. So let's look at the number 83, right? Just for instance. And so if you look at the number 83, let's look at the number 283. So 283, if we do this process, so the process that we're going to do is we're going to mod by 10, right? And we're going to get 3 out. And then what we're going to do is we're going to divide by 10. And remember, this is going to be integer division. So we're going to get 28. So that gives us the number 3, so that gives us the first digit. And then we're going to do that again. So mod by 10, we're going to get 8, so the next digit is 8, and then divide by 10. And then we're going to just get the number 2 left over. And then we mod by 10. We get 2. And then we divide by 10. We get 0. And that's when we know that we're done. So to convert it to binary, you do the same thing, except instead of dividing by 10 and modding by 10, you mod by 2. So for instance here, 283 mod 2 is equal to 1. And then we divide by 2. When we divide 283 by 2, what do we get? We're going to get 283 divided by 2. It's 141. And so remember, this is integer division. So we ignore all of, if we divided, actually it's 141.5, but we just divide it like that. Okay, so then what do? We do the same thing. So we say 141 mod 2. Whoops. 141 mod 2 is equal to 1. 141 divided by 2 is equal to 70. Now here what we do is we say 70 mod 2 is equal to 0. 70 divided by 2 is 35. Right? And so then we just keep doing this process, right? We say, okay, 35 mod 2 is 1. 35 divided by 2 is, well, whatever it is. So 34 divided by 2 is 17. And then what you do is you keep going. So 17 mod 2 is equal to 1. 17 divided by 2 is, I guess, 8, right? Because it's 16 divided by 2. And then 8 mod 2 is 0. 8 divided by 2 is 4. 4 mod 2 is 0. 4 divided by 2 is 2. 2 mod 2 is 0. 2 divided by 2 is 1. And then finally, 1 mod 2 is 1. 1 divided by 2 is 0. And this is not a bunch of factorials. And then we stop. So when we write out this number, technically you can start with the 0, but then you read backwards. So basically what you do is you go 0, 1, and then you read off the mod results. So it's going to be 1, 0, 0, 0, 1, 1, 0, 1, 1. And so is that actually 283, right? Did we calculate the binary expansion of 283? And so let's add all these things together. So this is the ones place, so 1 plus 2. This is 4, 8, 16, 32, 64, 128, and 256. So 256 plus the 32's, is it 32? No, it should be 16's place, right? 283. So 256 plus 16 is 272, plus 8, which is 280, plus 2, which is 282, plus the last one, which is 283. So remember that I'm going to put a little underscore b to mean binary here, and I'm going to say that that's equal to 283 underscore d per decimal. Would it be best to put this in a while loop? That is absolutely what you do. So what you do is you say, while number is not equal to 0, so what you do here is you say, what do you do? I guess, so there is one edge case. So if the number is equal to to 0, just return 0. You might understand why I do this edge case in a minute, but whatever, don't worry about it right now. So while the number is equal to 0, while the number is not equal to 0, what we're going to do is we are going to do our process. So we're going to say, if the number mod 2 is equal to 1, then do something else, right? And then what this means is that the number mod 2 is equal to 0, and we'll do something else. And then the last thing that we do is we take the number and we integer divide it by 2. And so what are these things that we're going to do? And so this is one way to think about doing it. You could always do like binary string plus equals 1, and here you could do binary string plus equals 0. But I caution you, because if we print out binary, or I guess decimal to binary, yeah, and we do 6, this is going to print out things in the reverse order, right? So 6 is actually 110, but here it's printing out 011. And the reason why it's doing that is because when we mod by 2 the first time and then divide by 2, the first digit actually goes on the front, right? So this is backwards, because we want the first digit to go onto the back, not the front. We want each digit to go onto the front, not the back. Because when you do the second digit, then it's going to go onto the back. It's always adding itself onto the back. So in order to prevent this, what I'm going to do is I'm just going to do, we want it to go onto the front. And so this is a little weird. It's different construction, right? This is not plus equals, because plus equals is going to do the same thing as, and that's not what we want. We want bigger digits to go left, not right. So, okay, so that's basically the explanation of what we're doing with these 2 lines of code here. But anyway, so let's run it now. There we go, 110. Let's whoops. So let's convert some numbers. Let's convert 6 again, just to double check. Let's convert 15. So 15 is 16 minus 1. And so because 15 is 16 minus 1, it's going to be all 1s, right? It's going to be 4 1s. Same thing with 3. Same thing with like 31. Same thing with 127 or 2047, right? They're all just going to be 1s. So this is all correct. And then let's try some things that are a lot of zeros. So for instance, 192 should just be like a 1100000 thing. Yep. How about 827? I have no idea what this is going to pop out. And so the question is this 827, right? And we ask ourselves that question. We say, this should be, let's pretend like this is in the 512 spot. So this is 512 plus 256. So that's 768. 768 plus, I guess it would be what? Is this, so this is 0, 2, or I'm sorry, 1, 2, 4, 8, 16, 32. So this is in the 32 spot. So basically what we do is, I'll just even show you my calculation. This is going to be 512 plus 256 plus 64 plus 32 plus 16 plus, okay, I did that wrong. So 512 plus 256, that's right. This is in the 128 spot, the 64 spot, so actually it's only 32 that we add, 16, 8, and then 2 and 1. There we go. So that should get us to 827. It's difficult because you have to count the number of places that you are, right? And binary numbers can get very large, or I should say very long. Yeah, so if you do 1,000, what is 1,000 going to be? 1,000 is going to be 512 plus 256 plus 128 plus 4. So it's going to be 111, a bunch of zeros, a 1, and then 2 zeros. Oh, I'm sorry, not that. It's going to be 64 plus 32 plus another 4. So it's going to, okay, so it's going to be like 11011000100. Yep. So this is basically how to convert from decimal back to binary. Okay. So all right, that's good news. Okay. Let's think. So now we've done binary to decimal and we've done decimal to binary. There's also some internal Python keywords, for instance, bin. So if we do print let me just show you. So 772. So you see that our number is the same as their number. The only difference is that they have a 0b in front of it. So 0b just means binary. So we could make our number the same way if we just said 0b plus. You know, 341, 201, 123, that kind of thing. So 12,123. Yeah, sure. Basically, remember that it's a string, so the 0b means binary, right? You want a decimal value? Oh, so for floating point numbers, they're different. You can't represent, so this process you can use to represent them, I guess, but not really. I mean, there's two ways to kind of do floating points in binary, and I'm not going to discuss that right now because it's a bit complicated, actually. So the way that computers do it is they use something called floating point, which is actually basically scientific notation. So what they do is they say, okay, like they represent a number as essentially 1 point something, and then they give it a, or actually I think they actually do it as 0 point something, and then they give it to a power. And so basically a floating point number has two different binary expressions. It has an integer power, and it has a what's called the mantissa, which is a like decimal expansion in binary. But it's, I shouldn't say a decimal expansion. It's an expansion on the other side of the point, on the like I guess the decimal point, right? So it's basically like if you had a number like 100.0101, something like this, then this would actually represent, so this represents 4, right? Because this is the 1, 2, 4's place. So this represents 4 point, and then this is 1/2, 1/4, 1/8, and 1/16. So this is basically 1/4 plus 1/16, so 0.25 plus, I guess Why am I teaching binary? Well, I mean, the reason why I'm teaching binary is because this is a computer science class, and for the rest of your computer science career, you will need this stuff. And so I'm not. We tend to ask a question or two about binary, but I'm not going to say it's like going to be useful in every single assignment. But you're going to need it for the rest of your life. So, so that's why we're teaching it. Okay. So now that everybody loves binary, and here is the algorithm that I coded up. So actually, I think this algorithm might not work with 0, this little bit of code here. But on the other hand, it does fit nicely onto a slide. So, okay. So let's ignore all this bitwise stuff. Nope, not going to talk about it. Nope. Not going to, I don't know what this is. We're not going to do this either. What I want to get to, okay, I really don't care about any of this stuff. What I want to get to, wow, where is hex? I had a lot of extra stuff in this presentation. Where is hex? Come on, hex. Wait a second. Hex isn't in here. Okay, I need to get the other set of slides. All right, let's go to the next set of slides. Yep. I guess I must have done it separately. Yeah, I did binary here, and then I did hexadecimal in lecture 19, I guess. Who can really explain what it is that I do? I do crazy things. So, basically, hex is base 16. And so the reason why hex is base 16 is because hexadecimal is, basically the way to say it is that hexadecimal is equal to the 6 plus 10 base, so 16. And so the reason why we use 16 is because, as you can see, if we do some of these examples, right, if we convert, say, 5 million, if we convert 5 million into a binary number, we see that this number is just gigantic, right? And so hexadecimal is like a standard way to just shrink down the number of digits or number of hexets or whatever that we write. Because here we have a ton of bits, probably something like 20 bits, so that's a lot. But we can shrink this number down and still keep most of the binary values. So, so basically, here's a table. And let me show you why this table is something that we already technically know. Basically, so 0, binary 0000 is 0. Binary 0001 is 1. Binary 0010, that's the 10 joke, 2. 0011, that's 3. 0100, that's 4. 0101, that's 5. 110, that's 6. 0111, 7. 1000, that's 8. 1001, that's 9. 1010, so that's 2 plus 8, which is 10. But we don't have a single digit that represents the number 10, right? We have the characters 1 and then followed by a 0, so that puts a 1 in the tens place and a 0 in the ones place. So the point is that we can't represent it as a single thing, so we invent the letter A to do it. Okay? And sometimes they'll use uppercase A, sometimes they'll use lowercase a, it really doesn't matter. It's just A. Same thing here. 1, 0, 1, 1. That's right, so you can actually say the number A, right? Where A is basically 10. And then B is going to be 1, 0, 1, 1, which is 11. 1, 1, 0, 0, we've already calculated that actually a number of times, so that's 12. And we use C to represent it. And then here we have 13, D, and 1, 0, 1, 1, 0, 1. And then we have E, 1, 1, 1, 0, 14, and F, 1, 1, 1, 1, 15. Okay. Yeah, it has to be converted back to... No, I'm saying it literally shrinks it down on the screen, right? Like, it's more readable for humans. When you convert, wouldn't ASCII A's be taken instead of 10? We're definitely going to be careful when we do that kind of conversion algorithm. Yeah, so hexadecimal is not for computer readability, it's for human readability. And let me show you some examples of... Yes. So let me show you some examples of converting. So this is how you convert some numbers. So let's say that we have a number like this. Let me show you how to convert. So let's go over here or something. Somewhere new. So here's a number. Well, I'm definitely not going to show you RGB using binary. I might show RGB using hex. So basically the rule is you divide into what are called nibbles, which are 4 bits at a time. And you should start from the, the right side. So go in from this direction. So this is what I mean. Here we go. So we're going to divide it like this. Okay? And then we look it up on our chart. Right? Or we just calculate. So here this is 8, 4, 0, 1. So 8 plus 4, this is 13. 13 is what? A is 10, B is 11, C is 12, D is 13. So this is D, or D. And 0011 is 3. So the hexadecimal number that we get is D3. Okay, so let's do it again. So here what we're going to get is, this is, 4 plus 1, so this is 5. This is 8 plus 2, so this is 10. And so remember that 10 is represented as A. And then let's do it again. Let's do some more stuff. So we say 1100, which is 12, I guess. So that'll be C. 0101, that's 5. 1000, 0111, 1001, 1111. So basically we just look everything up on the chart, right? This is C. This is 5. This is 8. This is 7. This is 9, I think. and this is F. So our hexadecimal number is C5879F. And so you see that hexadecimal is a way to shrink down binary numbers in a very, very efficient way. Now, here's the thing about hexadecimal numbers. Like, you can also convert them back to binary in the same way, right? So if we just do the opposite process using the chart, so how do we convert back? So let's convert, say, A32BF into binary. So what we're going to do, what if you had an odd number of bits? That's a good question. That is something I should address right now, so I'll address that. So if you had something like, yeah, so if you had 1001, so here's the trick. You add zeros until it has 8, or until it has a multiple of 4. So here we have this. So what you're actually going to do is you're going to go 0, 0, 0. Yep. And I mean, it's weird, but then you think about it and you're like, wait a second, why don't we write numbers like, I mean, is 183 equal to, say, and the answer is, like, I think so, right? We don't normally do it. It doesn't hurt anything, right? So basically, what you might call this is just your padding with zeros until it fits into the 4 paradigm. Yeah, they're technically unnecessary, but then you think about it and you say to yourself, like, it's easier to definitely read like this. So the reason why you might do this is because you're like, oh, well, when this converts into 1. Oh, okay, this is hexadecimal 19, right? Hexadecimal 19, right? In decimal, this is what? So this is 19 hex. In decimal, this is 1 plus 8, so 9 plus 16. So 9 plus 16 is 25, right? Because it's the sum of the two squares. So it's so this is one thing that's extremely confusing, is writing two different numbers. And so you see that here you have 19 hex, which is 25 decimals. So that, yeah, you always have to be careful with that kind of stuff. Yeah, so for computers, someone's kind of jumped ahead of me. Instead of saying 0b for binary, you say 0x for hex. And so in most programming languages, if you type something where you say 0x19, the computer will convert this or understand this as a hex number. Okay? All right. So let's keep going. Why is it X and not H? Historical reasons. That's all I can really say, is that when the decision was made, when some random programmer chose it or whatever back in the day, actually, let's look that up. Why is hex 0x, not 0h? Why are hexabit blah, 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 blah? Okay, so Stack Overflow says it was arbitrary. Well, so the thing is, you don't even need to convert. So for instance here, let me show you what Python is going to do. So if I just print out, let's say I print out So the computer understands these numbers as just numbers, right? So an integer is just a number stored as binary. So whenever you declare these numbers, right, this is an integer stored as binary. This is an integer stored as binary. This is an integer stored as binary. Now we're writing them in Python as hex, but remember that computers only ever understand binary. So the point is that it always, like, pretend like the computer has to convert, just like it has to convert, for instance, 25 into binary, 87 into binary, and 4095 into binary. It has to convert 0x19 into binary the same way. Yes, that is correct. So generally when you see those kinds of errors, a lot of like 0x type errors are memory problems, where 0x and then you have like some stuff is a value in RAM. It's a position, I guess, in RAM. Or it's an error code or something like that, but a lot of times it's a hex value representing a position in RAM. I think that's true about 75% of the time. So Python understands this language here. The computer doesn't understand why we're doing this, right? The computer's like, this was the same number as this, why are you printing it out again, right? The computer doesn't see these as different things. It sees them as the same thing. Okay, so let's convert A32BF into binary. So I'm sorry, yeah, no, I was right. So I'm actually going to use the 0x prefix here just to get us into the habit. And so what we're going to do here is we're going to say that this is equal to 1010 by the table, 0011, 0010. B should be 1011. F is going to be 1111. And so just like with numbers, like in decimal, so, with numbers in decimal, we usually go, say, 186,282. We separate these numbers by, or like 299,458. We separate them with a comma, or in some other places you separate them with a period, but I'm going to use commas to represent, decimal point is period, separator is comma. So the idea here is that, like, we use the comma to separate various sequences of digits, and so a lot of times it's traditional, at least when you're writing stuff out like on paper, it's traditional to kind of separate the nibbles by a space. And you see how that kind of improves readability, because if you don't do that, then what's going to end up happening is you're going to get a number like this. And that is kind of impenetrable, I think. It's very difficult to read and understand. So, okay, so we've converted... Yeah, same logic for phone numbers. You don't want to... Though I think in Britain, you'll sometimes see just like a complete blob of numbers just like thrown at people. And their phone numbers are longer than ours too, so it's... I don't know how they remember it. They're like, oh yeah, just dial blah, 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 blah. It's like 12 numbers or 18,000 numbers or something like that. I was like, I don't understand how they do it. I couldn't remember that many numbers, shouted at me that fast. But I guess maybe with practice you could do it. So, okay. So yes, that's what I was saying here. You can convert a number and you split it. All right. So So converting between hex and binary are pretty simple. Converting between hex and decimal, now that's difficult. And converting from decimal to hex, that's difficult. The reason why it's more difficult is because with hex, 2 to the 4th power is 16, right? So what that means is that each binary or each hex digit, each like hexit, or what we usually call hexadecimal digit, which is, you know, whatever, is exactly 4 bits. But you see that base 10, right? In binary, 10 is 1010, so that's not exactly anything, right? So it doesn't really get you anywhere. And the base 10 in hex is just A. So again, that doesn't really tell you, it doesn't get you where you're going, is what I'm saying. It's basically like, it's kind of in the middle, so it's sort of weird. Wouldn't we use a function in a function to convert decimal to binary? You don't need to. So to convert decimal to binary, well, we've already talked about how to do that, right? Decimal to binary I've already coded. So let's code hex to decimal. So hexadecimal is going to have to take a hex string. I mean, yeah, you could always do, like, convert from decimal into binary and then convert from binary into hex or something like that. You can always go through binary. You know, you can do it that way. Let me just show you how to convert. So we can change this, or is this decimal to hex or hex to decimal? I think this will do decimal to hex first. And we'll take a number. So basically, in order to do this conversion, if the number is 0, we're going to return 0. I'll return 0x0. Okay, and then let's just change it to number so that I don't have to rewrite everything. Okay, so then while the number is not equal to 0, what we're going to do is we are going to say number mod 16, right? And let's make a little dictionary. So the dictionary is going to be that 0 is the string 0, 1 is the string 1, 2 is the string 2, 3 maps to the string 3, 4 maps to the string 4, 5 maps to the string 5. This is not very interesting, but I'm going to do it anyway. 6 maps to 6, 7 maps to 7, 8 maps to 8, 9 maps to 9, but now 10 is going to map to A, 11 is going to map to B, 12 is going to, oh, I'm sorry, that should be 11 there. 12 is going to map to C, 13 is going to map to D. I'm basically just reproducing our chart. 14 is going to map to E, and 15 is going to map to F, and then we are good. Let's just call it, yeah. There we go. There we are. Yeah, but then you'd have to do an extra if statement, like if it's a number, just map to the number. This is just, this really simplifies everything, at least for me. I think this is probably the simplest way to do it. So let's see if I've done it right. So we're going to print out maybe, let's actually do it this way. Decimal to hex, and then we will print out hex of that number. And we don't need this anymore because it's going to print it out for us, so let's do it. Okay, let's convert 57. Well, first let's convert 64. 64 should be what? I guess 0x, it should be like 20? No, 40. 40, yeah. Oh, wow, okay, so I did that wrong. That should fix that. Okay. There we go. Perfect. 128. 77. 34. 123,456. 8392. All kinds of stuff, right? So basically, you see that hexadecimal numbers are always going to be like less than their counterparts in decimal. Yeah, something like that. Oh, guess it had a space in it. There we go. So, all right. Okay. So then there's one last thing to do. What is that one last thing to do? The one last thing to do is to convert back from hex to decimal. So this will be a hex string. So what we'll do first with the hex string is we'll hit it with dot lower. It certainly does not. Project 1 does not require any hex conversions. No. Okay, so then what we're going to do is we're going to go through and we're going to say, I guess, for character in, I don't know, maybe for I in range len of a hex string. So we're not going to pass it the full string. Maybe we'll we'll split that off. So what we're going to do now is we're going to say, okay, there we go. We're going to say value plus equals, and then we should have a reverse dictionary, right? We need the reverse dictionary, where instead of values now we'll have strings. So actually, I guess, well, no, we'll just do it this way. So let's do more stuff. 4, 4, 5, 5, 6, 6, 7, 7, and then 2 more lines of this. Let's do 8. That's 8, 9, 9, 10. Oh wait, no, I'm sorry. A, 10. Unfortunately, no, because The problem is that if you can't really get a value, or you can't get a key based on its value. You can only get a value based on its key. So you kind of have to flip everything. Unless I'm totally crazy. Maybe there's like a reverse function or something, but... okay. And then, so here what we're going to have to do is we're going to say... so this is going to be the confusing part. There we go. I think that should be right. So let's input a string. And then we're going to hexadecimal it. Okay. And so, yep, okay. There we go. And then how do we convert this to decimals? So I guess we can say does int do that? I don't know. I bet it doesn't. So what if we do 0x11? So wait, why did that terminate? Oh, because we need hex string. So yeah, it won't let us do it. But anyway, let's just run this. Okay, what's our hex string? That's not right. Oh wait, yes it is. Oh my god, I thought it was binary. I was like, how did I not get 3? But why is this 17? It's 17 because it's 16 plus 1, right? So is this 174? This should be 160 plus 14, so yes, that's right. 255, right? Because that's, if we do 256 is this, 255 is that. So, yep, so this will do it. Keep in mind that we have to take from the back of the string, so we're kind of like reversing it. That's what this does. So this goes backwards in the string because it takes us from the length minus 1, which is the last thing in the string, all the way down to 0 by subtracting. And then the power that each one has is 16 to that power. So that's basically how that works to convert. All right, so I've gone over by about 10 minutes. So there's no DEC, unfortunately. This is what you get. So I'll let everybody go, but maybe I'll do hexadecimal to decimal I'll review this in future lectures, because I don't think I covered it perfectly, just because I kind of ran low on time. But anyway, we will terminate the lecture at this point. It's not on the GitHub. It's, you know what? I posted it on the GL server, and I posted an announcement on Discord about it. But I'll just post it on Discord, and I'll send out an announcement with it because I've gotten that question too many times. All right. Have a good day, everyone.